Step quietly into the shadowy depths of the quantum world, a place where reality behaves unlike anything we see in daily life. Here, particles pop in and out of existence, waves become particles, and time itself sometimes plays tricks on cause and effect. This is a realm where the familiar laws of classical physics dissolve into astonishing oddities, where entangled twins can communicate faster than light, where photons choose their past based on future choices, and where matter can vanish through walls it should never pass. Tonight, we journey through the strangest quantum phenomena ever discovered, bizarre effects that have challenged scientists and philosophers alike, shaking the foundations of what we think we know about space, time, and existence itself. Prepare to enter a world of paradox, mystery, and breathtaking wonder, where the impossible is every day, and the universe reveals its deepest secrets, one astonishing experiment at a time. Quantum entanglement, the spooky thread across the universe. Close your eyes and picture the deepest midnight sky, scattered with stars billions of years old, a vast, cold emptiness that feels infinite. Now imagine two particles, born together in a flash of creation, flung to opposite sides of the universe. As you watch, something impossible happens. What you do to one, the other feels instantly, faster than any signal could possibly travel, as if they remain bound by a secret handshake written into the cosmos itself. This is the enigma physicists call quantum entanglement, Einstein's notorious spooky action at a distance. The origins of quantum entanglement are tied to the roots of quantum mechanics itself. In the early 20th century, scientists unraveled one unsettling fact after another. Particles weren't just points in space, but clouds of probabilities, both here and there, neither alive nor dead until someone looked. Yet within these clouds, stranger things lurked. In 1935, physicists Albert Einstein, Boris Podolsky, and Nathan Rosen challenged quantum theory with a puzzle, now called the EPR paradox. Their argument: if quantum mechanics was true, then a particle and its twin, once linked, could influence each other's fate instantly, no matter how far apart. Einstein, ever the champion of common sense, scoffed. Spooky action at a distance, he called it, a concept too bizarre even for him. Erwin Schrödinger soon after gave the phenomenon its name, Verschränkung, entanglement. He saw it not as a bug, but the ultimate feature, a new, bewildering ingredient in nature's recipe. Imagine two particles, photons or electrons, meeting in a perfect collision. Their properties, spin, polarization, or momentum, become entwined in a dance so subtle that once they've parted ways, they are never truly alone. Their quantum states can no longer be described as separate stories. They are chapters in the same book. Even when miles or even light years apart, their connection remains. To an observer, it works like this. If one particle is measured and found to spin up, its twin, wherever it is, will instantly show down. No matter how you arrange their separation, what happens to one is mirrored by the other, defying the normal rules of cause and effect. It's essential to understand entanglement is not a signal, not a message flying between particles. It's a correlation deeper than space, a kind of cosmic agreement signed in silence. Decades of debate, paradoxes, and ingenious thought experiments followed Einstein's challenge. Experts argued hidden variables existed, tucked away beyond our measurement, governing these spooky effects. Surely nature would not be so flagrantly illogical. But in 1964, physicist John Bell imagined a test. For the first time, a way to probe whether entanglement was just a math trick or a fundamental property of the universe. Bell's theorem proved that if quantum theory was right, Certain experiments with entangled particles would show correlations no hidden variable could explain. The actual experiments soon followed. John Clauser, Stuart Friedman, Elaine Aspect, and others sent photons down different paths and measured how their properties aligned or diverged. In lab after lab, the results shattered classical explanations. No matter how they tweaked the settings, outcomes fit quantum predictions, and quantum predictions alone. Particles, it seemed, truly did maintain a connection that distance could not break. The universe, at its smallest scale, refused to be local and predictable. Now, entanglement is not just a philosopher's curiosity, but the foundation for 21st century technology. In laboratories, scientists create entangled pairs using special crystals, even sending them through fiber optic cables across cities and between satellites and ground stations. Quantum entanglement powers quantum cryptography, guaranteeing unbreakable messages. If a spy tries to eavesdrop, the act disrupts the entanglement and gives them away. It's the engine of quantum computers, letting unimaginable computations unfold with fewer atoms than a pinhead could hold. And yet, for all its technical marvel, entanglement remains an unbroken riddle. Midnight conversations among physicists still return to the same hushed awe. Why does the universe allow such a thing? How can two distant objects be so deeply one? To understand entanglement is to loosen our grip on everyday logic. Normally, to know about an object, you'd study it directly, touch a stone, measure a shadow. With entangled particles, every attempt to pin down one reveals information about the other, but also dissolves their shared state. The whole is more than the sum of its parts. Physicists say that entangled systems cannot be described by the multiplication of their separate states. Their wave functions, mathematical blueprints, become a single mesh. They do not have independent properties. Their reality is relational, defined only together. Another unsettling truth: observation destroys the magic. To see or measure one entangled particle is to break the link. The connection is delicate, disrupted by even the gentlest brush with the outside world, what physicists call decoherence. But perhaps the greatest marvel of quantum entanglement is the way it forces humility. The universe, it seems, does not need to make sense to us. Its logic may be written in rhythms beyond our perception, joining distant pieces in ways even Einstein could never bear to imagine. And yet this strange behavior is real, measurable, repeatable, essential to the deepest architecture of reality. And yet this strange behavior is real, measurable, repeatable, essential to the deepest architecture of reality. For the first time, physicists must live with a universe that is not only odd, but fundamentally interconnected at levels space and time cannot divide. To truly appreciate quantum entanglement, leave behind the spreadsheets and diagrams for a moment. Instead, imagine two dancers spinning miles apart, each knowing the other's steps. Neither can move without guiding the other's motions. Or envision two lovers separated by oceans who still finish one another's sentences, bound not by letters or phone calls, but by the law of the cosmos itself. Entanglement's lesson is at once simple and profound. Reality, at its finest threads, is woven together. The fates of distant things, each thought, each star, each atom, may be more closely linked than we can ever understand. There is no strict border between here and there. For those who dream of infinite possibility, entanglement is a portal. Could it one day allow teleportation? Already, quantum teleportation experiments swap information rather than matter, hinting at sci-fi futures made suddenly plausible. Could entanglement offer new clues to space, time, or even the nature of consciousness? Some physicists whisper yes, though definitive answers still shimmer tantalizingly out of reach. Quantum superposition. Imagine you're alone in a silent room, a single shaft of light sneaking through the door. You reach for a coin, flip it into the air, and before you catch it, the world waits. Heads or tails, fate uncertain. But in the quantum world, reality goes further. That coin can be both heads and tails at once, a shimmering blend of every possibility. This is the strange truth of quantum superposition, a truth that stretches the imagination and rattles the foundations of our intuition. In the early 20th century, as physicists probed the fabric of the atom, they found something astonishing. At the smallest scales, nature did not abide by the rules of certainty. Instead, particles like electrons, photons, and atoms could occupy all their allowed states at once, only choosing a definitive one when someone or something measured them. This shimmering coexistence is called superposition. Picture a quantum system, a particle, say, with two possible states, A and B. Classically, it must be either A or B, like a light switch that's either on or off. But in quantum mechanics, the particle exists in a superposition, an eerie blur between A and B until the moment of observation. When measured, the haze collapses to reveal only one state, but until then, reality is richer and more mysterious. To see superposition in action, consider the double slit experiment, a playground where matter's duality dances in plain sight. Shine a beam of light or fire electrons at a barrier with two slits and watch the pattern that emerges on the screen behind. Classically, you'd expect two bands, one from each slit, but what happens is an interference pattern, many bright and dark lines, as if each particle travels both paths at once and interferes with itself. Now send just one particle at a time, wait for it to finish before you send the next, and still over time the interference pattern emerges. Even a lone electron, it seems, must go through both slits at once, superposed in multiple possibilities. Measure which slit it passes through though, and the interference vanishes. The curtain drops, and quantum magic gives way to classical certainty. Now step into the mind of Erwin Schrödinger. To highlight how bizarre quantum rules can be, he imagined a cat sealed inside a box with its fate tied to a quantum event, a single radioactive atom. If the atom decays, it triggers poison and kills the cat. If not, the cat lives. According to quantum mechanics, until you open the box, the atom is in a superposition of decayed and not decayed. By extension, so is the cat, alive and dead simultaneously. A powerful and unsettling illustration of quantum principle trickling up into our macroscopic world. Schrödinger's cat isn't just a riddle for scientists, it's a caution against blindly extending quantum weirdness to the everyday. Yet experiments with small particles, not cats, do show that superposition is very real at the tiniest scales. It isn't just philosophy, it's experimentally verified. In 2019, physicists managed to put molecules composed of nearly 2,000 atoms into superposed states, pushing the boundary between quantum and classical worlds ever farther. Laser-cooled ions, superconducting circuits, and photons in quantum computers all routinely enter superposition, their states blending possibilities until measurement forces a single outcome. In labs worldwide, physicists have sent entangled photons and ions into networks where their superposed states enable quantum computers to solve problems unreachable by classical machines, demonstrating that superposition isn't just strange, but practical. With all this magic at the atomic scale, why can't you see your coffee mug in two places? The answer is decoherence. Quantum states are fragile, easily disrupted when their environment, air molecules, photons, vibrations, interacts with them. Such noise collapses the superposition into classical certainty. Only in careful isolation, or with delicate error correction can scientists sustain superposed states for long? Superposition also forces us to confront a profound question. What role does observation play in reality? In some interpretations, observation picks one outcome, collapsing the haze of possibility into a definite world. Others argue that all outcomes persist in a branching many worlds universe, a cosmic superposition of entire universes. What's clear is that quantum superposition blurs the line between the possible and the actual, making the act of observation fundamental to the outcome itself. At its heart, superposition tells us something breathtaking. Reality, beneath its smooth surface, is made of probabilities, not certainties. Before the coin falls, it hangs in the air, 1,000 possibilities, all real for just a moment. Your smartphone, your computer, MRI scanners, and even the sun's shining light all owe their power to superposition. Yet outside the lab, its paradox lies mostly hidden, a secret woven into the quantum fabric underneath everyday experience. Wave-particle duality, the dance of light and shadow. Imagine yourself kneeling on a quiet beach at dusk. The surface of the water glows in the fading light, gentle ripples weaving ever-shifting patterns against the shore. Now, with a child's curiosity, you toss a small stone and watch concentric waves ripple outwards. Their shapes meet, overlap, build peaks, and sometimes erase each other entirely. A mesmerizing demonstration of how waves combine, sometimes amplifying, sometimes cancelling, always in motion. But what if the wave is not just water or sound, but the hard, gleaming stuff of reality? Light, electrons, even atoms. What if, beneath the world's solidity, lies a restless shimmer where things can be both particle and wave, where even a single quantum object seems to move through more than one place at once? This is the heart of wave-particle duality, and at its center lies the famous double-slit experiment, perhaps the strangest, most humbling puzzle in all of physics. For centuries, the true nature of light was fiercely debated. In the 17th century, Isaac Newton saw light as a stream of particles, corpuscles darting through the void, bouncing and scattering. His contemporary, Christian Huygens, insisted light was a wave, rippling through the ether as sound does in air. For a time, Newton's authority prevailed, particles won the day. But then, in 1801, Thomas Young shattered this certainty. He fashioned a simple experiment: shine light through two thin slits, side by side, aiming at a screen beyond. If light were indeed composed of tiny balls, you'd expect to see two bright bars, direct shadows of the slits themselves. But what emerged instead was a striped, intricate interference pattern, bands of bright and dark light and shadow, clear evidence of waves overlapping and combining, reinforcing and erasing. Light, it now seemed, was a wave, rippling, spreading and blending. By 1865, Maxwell's equations locked this picture in place, showing that light is an electromagnetic wave moving through space at the ultimate cosmic speed. Just as scientists grew comfortable with light's wave nature, the 20th century dawned, bringing unexpected news. Max Planck and Albert Einstein, struggling to explain mysterious results in blackbody radiation and the photoelectric effect, reluctantly revived the notion of particles. Einstein showed that light sometimes arrives in indivisible quanta, packets of energy now called photons, knocking electrons loose in sudden bursts, not gentle waves. Waves and particles? Both? How could that be? The experiments kept coming, and each seemed to contradict intuition, but the evidence was clear. Sometimes light behaved as a continuous wave, sometimes it arrived as discrete, countable bullets. And then, the scientists turned the experiment on matter itself. If light can behave both as wave and particle, What of objects with mass, electrons, say, or even larger things? In the 1920s, de Broglie speculated, almost in a whisper, that every piece of matter also has a wavelength, an elegant math mirroring light. Soon, physicists built new experiments. Fire electrons, a fundamental building block of atoms, one at a time through a double-slit apparatus, expecting to see two patterns, two clusters behind the slits. But no, over time, even with just one electron at a time, something magical and impossible emerged, an interference pattern, the very hallmark of waves. It seems, impossibly, that each electron travels not through one slit or the other, but through both, interfering with itself as if it is a wave spread through all possibilities. Yet paradoxically, when a detector watches to see which slit the electron passes through, the interference vanishes. The electron then behaves like a particle, forced to choose a path, and the wavy dance disappears. The double-slit experiment is more than a trick. It exposes a rift in the fabric of reality, where observation itself shapes what is real. Measured and watched, nature collapses into concreteness. The electron lands in one place, not many, and the wave of possibility shrinks to a single outcome. Left unmeasured, it remains an ethereal haze, both here and there, both heads and tails. No one, not even the great architects of quantum theory, could quite believe it. Is the moon there when no one looks? Einstein asked, skeptical and troubled, for such a universe grants the observer unfathomable power. Niels Bohr, Werner Heisenberg, and the quantum founders responded. The experiment decides the answer. Reality is not made only of things, but of questions, measurements, and probabilities. The universe, at its base, is a conversation. What we ask helps shape what is possible. In the decades since, the double-slit experiment has become physics' most storied riddle, repeated with single photons, electrons, atoms, and even molecules thousands of times heavier. Always the same lesson: the quantum world refuses to divide cleanly into waves or particles. It composes existence out of haunting, flickering possibility. And the larger the object, the harder it is to keep the interference pattern intact. Environmental noise, air, heat, or any disturbance forces the system toward classical certainty, erasing the delicate quantum effects in a process known as decoherence. Thus, you cannot pass your hand through both slits or be in two places at once. The magic lies where the world is small, cold, and quiet. Wave-particle duality is not just a curiosity. It pulses through every quantum device, every atom in your body, every photon shining in your eyes. Your very existence at the molecular level is sculpted by quantum interference, by the strange principle that things can be multiple, undecided, and whole until a choice, an observation, is made. Philosophers and physicists alike still puzzle over what this all means. Does the act of measuring create reality? Is there a many worlds universe where every possibility is realized, branching endlessly? Or does consciousness itself play a special cosmic role in collapsing the wave of possibility? No single answer satisfies all. The double slit stands enduring, not solved, but wondrous, forever inviting new generations to stare into its patterns and ask, what truly is the nature of reality? Quantum tunneling, when particles walk through walls. As you settle into darkness, picture a landscape smaller than dust, smaller than atoms, a quantum world where familiar rules shudder and reality behaves as if it were pulled from the pages of a dream. You're about to witness an escape act worthy of a master illusionist, where barriers become mirages and the impossible unfolds a billion times each second. Welcome to the bizarre domain of quantum tunneling. In our everyday world, barriers are final. If you roll a ball toward a hill that's too steep, it stops cold. Lacking energy, it cannot summit the crest, much less appear on the far side. This you trust with every step and every fortress wall. Cause and effect, certainty, the classical march of logic. Now shrink down to the quantum scale, where the players are electrons and protons, photons and atoms, entities not so much solid shapes as drifting clouds of probability. Here, effects don't always follow the logic of the larger world. Sometimes a quantum ball approaches a barrier it cannot, by all classical calculations, cross, and yet miraculously appears on the other side. No climbing, no crashing, no pounding through, a soft dissolving, as if the wall were never quite real. This is quantum tunneling, nature's audacious loophole, a phenomenon as real as your own heartbeat, essential to the inner workings of the cosmos. To see why quantum tunneling stuns physicists, consider the strange rules governing particles at the smallest scales. In quantum mechanics, the position and energy of a particle aren't fixed, but fuzzed out into wave functions, mathematical clouds that describe where the particle might be found and with what probability. Now, imagine a particle approaching a barrier, say a thin membrane or a region of higher energy than the particle possesses. According to classical physics, it should bounce back. The quantum wave function, though, doesn't plunge to zero at the barrier. Instead, it decays, seeping under and through. If the barrier is thin enough, or not infinitely high, there remains a non-zero chance, tiny but real, that the particle's wave function leaks to the far side. If you look for the particle there, sometimes you'll find it, a spontaneous jailbreak, an act that defies every stone and mortar instinct. No energy is lost or gained. The leak happens because, at the quantum level, existence is never wholly confined. Certainty is always replaced by possibility. Quantum tunneling might sound like a theory, an oddity for physics textbooks, but tunnels run through reality's foundation. Without them, no stars would shine, no electronics would function, no life would spark. In the heart of the sun, atomic nuclei need to overcome the fierce repulsion of their positive charges, the so-called Coulomb barrier, to fuse and release sunlight's energy. At the sun's temperature, classical physics says fusion should almost never happen, but quantum tunneling offers a shortcut. Protons, acting as fuzzy waves, slip through energy barriers, enabling nuclear fusion to power every sunbeam that warms our skin. Your body too depends on tunnels. In enzymes and proteins, electrons hop across molecules, sparking essential chemical reactions. Even the fire that burns or the food you digest owes its existence to tunneling's subtle magic. Tunneling doesn't just rule distant stars or living cells, it shapes the very heart of modern technology. Consider the tunnel diode, invented in the mid-20th century by Leo Osaki. This tiny device leverages tunneling. Electrons flow across junctions that, in classical theory, should be impenetrable, creating swift, ultra-sensitive electrical responses. Without tunneling, your phone, computer, and every microchip would be little more than just expensive sand. Modern electronics shrink their components until quantum effects dominate. Engineers must embrace the tunnel, not fight it, to keep pace with progress. In quantum computing, tunneling is the lifeblood of quantum bits, or qubits. These fragile quantum states tunnel between energy levels, enabling calculations simultaneously across myriad possibilities. Technologies born from tunneling have revolutionized science. The scanning tunneling microscope, for example, images individual atoms and molecules by exploiting tunneling currents between a nanoscopic tip and a sample surface, a feat unthinkable by classical means. Physicists and material scientists can map the contours of matter even coaxing single atoms into new arrangements, all thanks to electrons that disregard classical boundaries. In astronomy, tunneling explains how radioactive atoms decay, firing off particles that, classically trapped, nonetheless appear outside the nucleus. This is why radiocarbon dating works, measuring time by tracking the statistical signatures of tunneling. But why does any of this happen? At the most fundamental level, tunneling arises from quantum indeterminacy, the universe's refusal to pin down every outcome in advance. At every moment, a quantum particle samples more than its immediate region. Its wave function, mathematically, does not vanish at the barrier, but stretches under, offering the tiny but persistent likelihood of escape. If you were the size of an electron, the world would become a series of foggy, permeable walls. Boundaries would be suggestions, not absolutes, and sometimes, standing at the base of a mountain, you would simply appear, as if by miracle, on the other side. Tunneling is most significant at scales where wave functions are broad and barriers thin, in essence, the quantum realm. For everyday objects, a baseball, a cat, the probability of tunneling through even a millimeter thick wall is so impossibly tiny, it might as well never happen, not in the life of the universe. But in carefully curated laboratory conditions, researchers have coaxed larger and larger objects, clusters of atoms, superconducting circuits, into behavioral regimes where tunneling's trace can be measured. Each time, reality bends, but doesn't break. The quantum world remains pliant, while classical certainty is always an emergent, approximate truth. Quantum tunneling reverberates far beyond physics labs. It teases the imagination. What does it mean for a universe to be fundamentally uncertain? To live in a reality where the impossible is routine, where walls become doors through the tiniest cracks. It challenges determinism, bringing a flicker of profound unpredictability to the heart of existence. It whispers of chance, of possibility, of escape from prisons, both physical and conceptual. In literature and art, tunneling has become a metaphor for hope, for the invisible avenues through which change and possibility emerge, even when all signs say, no way through. The quantum measurement problem, where reality hangs in the balance. Picture yourself in a silent lab just before dawn. Glass speakers glint under soft neon, and in the heart of this sanctum, a single particle, tiny beyond imagination, waits restlessly inside an invisible cloud of possibility. Is it here or there? Is it spinning up or down? The world holds its breath, for at this smaller scale, nothing is certain until you, the observer, look. Yet the very act of looking doesn't merely reveal the truth, it changes it. This is the strangeness at the core of quantum mechanics, the quantum measurement problem, where nothing is real until it is seen, and seeing changes the thing itself. In classical physics, the realm of Newton's apple and Galileo's falling stones, the world is solid, consistent, and predictable. Everything has a single position and momentum, determined and waiting to be discovered. Measurement is mere unveiling. The tree has leaves, whether you count them or not. But shrink down to the atomic and subatomic, and the certainties dissolve. In the quantum world, before measurement, particles are not in one place, but a haze of probability, a wave function that describes everywhere they might possibly be. The rules of quantum mechanics, enshrined in equations by Schrödinger and Heisenberg, tell us not where a particle is, but the odds of finding it in any location. Reality seems soft, blurry, and unfinished. Suppose you want to know whether an electron sits on the left side or the right side of a tiny box. Prepare everything. Set your detectors with superhuman precision. Before you look, the quantum recipe tells you the electron is not on the left or right, but in a superposition, a ghostly presence on both sides, its probability waving across the box. But the instant you measure, the electron is found on one side or the other, not both. The wave collapses. The spell is broken. The act of measurement doesn't simply reveal reality, it creates it. Niels Bohr and Werner Heisenberg called this the collapse of the wave function. Until observation, all potentialities coexist. Upon observation, the spread vanishes, and only one possibility remains, irreversible. No experiment shows the mystery more sharply than the double-slit experiment. Fire a barrage of photons or electrons at a pair of slits, and their arrival at the screen creates not two bands, but many, bright and dark, an interference pattern that proves each quantum travels through both slits at once, interfering with itself. But add a detector to peek which slit the particle passes through, and instantly the interference vanishes. The quantum chooses. It walks one path or the other. The simple act of observing changes the outcome, as if reality responds to the question with a new answer every time. Physicists realized early on that while the equations of quantum mechanics predicted every experiment with stunning accuracy, they were eerily silent about what exactly measurement meant. What is so special about the act of observing? Why should the universe, with all its blind machinery, care if you, a conscious observer, are watching? Some physicists argued that the measuring device, being classical and macroscopic, forced the quantum world to choose. Others speculated that consciousness itself sparked collapse, that the universe waits for a mind before becoming concrete. John von Neumann tried to formalize things. He saw that, mathematically, the measurement process could include the observer's brain and all their neurons as participants in the quantum dance. It was just quantum systems all the way up. So when exactly does reality gel into a single clear story? This led to Schrödinger's infamous cat, a feline both alive and dead, while its fate is entangled with a quantum event inside a box. Schrödinger wanted to show how absurd it was to take quantum superposition so literally at macro scale, but in decades since, experimenters have put ever larger systems into superposed states, shrinking the border between quantum possibility and classical fact. Some, like Hugh Everett, propose there is no collapse at all. Every measurement causes the universe to fork, one branch per possible outcome, where every quantum possibility is realized in a new world. In this many worlds view, the electron is found here in one universe and there in another, with each observer living through one thread of an infinite tapestry. Others favor decoherence, where interactions with the environment, air molecules, photons, vibrations, quickly destroy quantum superpositions. So the everyday world becomes classical by default. Yet even decoherence doesn't explain why you see one outcome and not many. For decades, some scientists wondered if consciousness is uniquely special in the measurement problem. Could the mystery be that the act of knowing collapses the wave function, bringing reality into focus at the level of the observer's conscious mind? Most physicists today are suspicious of this view, hesitant to tie the hard science of quantum physics to the soft science of mind. They point out that measurements are the same even for automated devices with no human watching. Still, a shadow of the question lingers, since consciousness, like quantum measurement, is weirdly difficult to define and stubbornly resistant to reduction. Physicists continue to tinker, devising ever sharper experiments. Weak measurements nudge systems gently, sometimes allowing glimpses of the quantum world without triggering full collapse. Delayed choice experiments suggest that choices made now can affect the way particles behaved in the past, retroactively changing the outcome. In 2019, scientists in Austria managed to put mirrors as large as grains of sand into superposed states, creating something like a tiny cat fuzzed between two possibilities before the act of measurement snapped it into one reality. Others attempt quantum eraser experiments, restoring interference patterns by erasing which path information, not only after the particle passes the slits, but even after it should have landed, challenging the flow of time itself. For all the technical progress, the quantum measurement problem remains one of science's deepest riddles. Is measurement an artifact of our ignorance, the point at which the math just stops tracking the true underlying reality? Is it a physical process woven into the fabric of space-time, or forever dependent on the presence of an observer, conscious or otherwise? Or is measurement simply a rule for updating beliefs, not a change in the world, but a change in what we know? Philosophers debate the meaning, physicists argue in late-night seminars, experimenters keep constructing sharper tools to probe the shadowy borderland. Each new answer seems only to deepen the questions. The quantum measurement problem is more than an arcane puzzle. It teaches humility about what we can know and how we can know it. Each time you peer into the mysteries of the atom, each time you flick a switch or glance at a starlit sky, you enter a universe where, at the smallest scale, facts are not simply discovered, but created, where the very nature of being is restless, fluid, and alive to the act of questioning. In the liminal space between possibility and fact, between wave and particle, between the seen and the unseen, reality waits, not as a static answer written in stone, but as a living question, ever shaped by the act of attention. The quantum Zeno Effect, when watching, freezes reality. Imagine peering into the smallest stage of all, where atoms flit and fade, where possibility outnumbers stars, and where the act of watching does not simply reveal, but transforms. Here, in the quantum world, a strange magic holds sway, the power to stop change with a glance. It's the quantum Zeno Effect, a phenomenon where the universe itself seems to freeze when observed too closely, defying the intuition of centuries and inviting new riddles at the intersection of science and philosophy. At the heart of this story lies an ancient puzzle, Zeno's arrow. In the 5th century BCE, Zeno of Elea argued that an arrow in flight is, at every instant, stationary, frozen, unmoving. If every moment is a still frame, how does the arrow fly at all? For millennia, philosophers pondered these paradoxes as curiosities of thought. But it was only in the 20th century, as quantum mechanics unfolded its wilder truths, that the paradox would re-emerge. Not as abstract poetry, but as testable physical reality. Physicists Misra and Sudarshan first framed the modern quantum Zeno effect in the late 1970s. They wondered, what happens if you measure a quantum system over and over in rapid succession? The mathematics revealed something deeply counterintuitive. If you check often enough, you can halt the evolution of a quantum state. The system, like Zeno's arrow, refuses to shift. Classically, measurement is passive. A thermometer left in water, a glance at a clock. Not so in quantum mechanics. At the atomic scale, measurement is an interaction, a force pulling a quantum system sharply toward one outcome. In the language of quantum theory, the wave function of a system, its cloud of potential, collapses when measured, snapping into a definite state. If a quantum system is left alone, it evolves naturally from one state to another. A radioactive atom may decay, an electron may jump from one energy level to another, a particle may tunnel through a barrier. But if you keep asking, are you still here? Are you still here? At intervals much shorter than the system's natural time scale, the answer always comes back, yes. The system has no chance to change before being reset by your observation. You freeze it in place by watching, just as Zeno imagined. The quantum Zeno effect isn't just theoretical, it's been seen in the lab time and time again. In 1989, physicist David Wineland and his team at NIST used thousands of beryllium ions stored and laser-cooled to create a real-world test. Ordinarily, a pulse of energy would have pushed these ions from their ground state into higher energy, but by shining ultraviolet light, effectively measuring them between each step, they suppressed the transition. The ions remained, resistant to change, frozen by the omnipresence of their observers. Subsequent experiments ramped up the strangeness. In 2001, Mark Raisin's group at the University of Texas manipulated ultra-cold sodium atoms in an optical lattice. By swiftly reducing the lattice's acceleration, they interrupted quantum tunneling, observing both the Zeno Effect and the anti-Zeno Effect. Even more stunning, in recent experiments with superconducting qubits and photons in optical cavities, the repeated act of measurement held quantum states steady, protecting fragile systems from their own restless dynamics. In 2015, Mukund Vengalator's group at Cornell verified that atoms trapped in a lattice could have their quantum tunneling entirely suppressed, proving that when watched, even the most restless particles grow still. The quantum Zeno effect boils down to this: if you observe a system frequently enough, you can prevent it from evolving naturally. It's not unlike the proverbial watched pot never boils, but in quantum mechanics, the maxim becomes literal physics, not just a metaphor. Imagine standing in front of a revolving door, checking every microsecond if your friend has entered. If each check resets their progress, they never pass through. The door stays closed, time after time. In quantum terms, the possibility waves keep collapsing into the no-change outcome. This effect is more than a curiosity. Quantum computers, the dream machines of the future, rely on fragile qubits, quantum bits that exist in superposition, simultaneously 1 and 0, alive with possibility. Yet qubits are slippery. They decohere easily, losing their quantum magic and becoming ordinary classical bits. The quantum Zeno effect provides a tool to stabilize qubits, suppressing errors and preserving the memory of fragile quantum information. By designing careful sequences of measurements, sometimes even weak measurements that may disturb the system only gently, researchers can freeze unwanted transitions and increase computation fidelity. The effect also offers a weapon against quantum noise, shielding systems from interference. It's like wrapping your most precious secret in layers and layers of gentle reminders, ensuring it is never lost or altered. Engineers and theorists now see the Zeno effect as crucial for quantum control, error correction, and quantum metrology, offering pathways to ever more stable and precise quantum technologies. But nature, ever playful, throws another twist. While frequent measurement locks a state, less frequent measurement, at just the wrong cadence, can accelerate change, enhancing transitions in a process called the quantum anti-Zeno effect. The balance between freezing and hastening depends on the timing and nature of measurement, suggesting a quantum world as dynamic as it is perplexing. So what really counts as a measurement? In the quantum world, the line is blurred. Any strong enough interaction, whether from a measuring device or environmental nudge, can collapse a wave function. Even the act of watching by stray photons in the air or the fields of nearby atoms can trigger the Zeno freeze. This distance between system and observer echoes deeply in philosophy. When does the world become real? What is the role of the observer? The Zeno effect places a question mark at the very boundary between possible and actual, a secret handshake between quantum law and classical experience. Once a philosopher's paradox, the quantum Zeno effect is now a working tool of modern physics. It is helping us build the next generation of quantum computers, probe the mechanics of life's tiniest engines, and even understand how certain birds may sense the Earth's magnetic field, with molecules in their eyes frozen by observation from their own biochemistry. The effect has been harnessed in commercial atomic magnetometers and is an area of active research for quantum simulations, memory stabilization, and timekeeping of extraordinary precision. The quantum Zeno Effect remains a humbling reminder of quantum strangeness. In a world where observation holds change, where watching can freeze possibility, physicists are forced to accept a universe in which the boundary between potential and actual is never absolute, and humans, as observers, leave fingerprints on the world simply by looking. Is the arrow flying, or is it always still? Will the atom jump, or will it remain, forever waiting, held in place by the gaze? The answer, in the quantum world, is both and neither, until the next measurement, the next question, the next mysterious dance between knowing and not knowing. Quantum vacuum, the energy in empty space. Close your eyes and imagine the deepest darkness between the stars, a region so cold and so empty that, to our senses, there is nothing. Yet, at the quantum level, this emptiness bursts with invisible energy and restless activity. Welcome to the quantum vacuum, a place where nothingness is never truly nothing, and reality is built upon a restless, seething field of possibility. This is the world of zero-point energy and vacuum fluctuations, the most enigmatic breath of the quantum universe. For centuries, vacuum meant void, absolute emptiness, absence, a stage swept clean of everything. In classical physics, vacuums were lifeless gaps, free from all matter and energy. But in quantum mechanics, every certitude crumbles. Here, emptiness itself becomes alive, a backdrop thrumming with invisible waves, ceaseless emergence, flickering potential. Quantum theory tells us that every point in space is filled with quantum fields, ever shifting, jostling, and vibrating. Even at absolute zero, the lowest temperature possible, the fields never fall still. They are animated with the irreducible hum of zero-point energy, the inescapable base-level motion the universe cannot silence. But why does this emptiness pulse with energy? The answer is woven into quantum law, specifically the Heisenberg uncertainty principle. In essence, the principle insists that there's a hard limit on how precisely you can know certain pairs of quantities, like a particle's position and momentum, or a field's energy and how quickly it changes. If you could freeze a quantum system perfectly, knowing both its position and momentum with infinite accuracy, it would violate the cosmic rule. Instead, everything remains blurry, smearing out even the quietest possible state. In this ground state, the so-called zero-point state, a tiny but unavoidable jittering persists. The energy of this state is not zero. It is the minimum amount the quantum world will allow, and it sits like a perpetual undertone beneath everything that happens. Extend this idea to the vacuum itself. In quantum field theory, every region of space is filled with a web of fields, matter fields for particles like electrons and quarks, and force fields for photons, gluons, etc. Vacuum in this frame is not empty space, but the combination of all fields in their lowest energy, or ground states. Even here, fields jitter, flicker, and shift. This is vacuum fluctuation, the transient, random, yet real changes in energy echoing through the void. Every so often, these fluctuations throw up virtual particles, pairs that appear out of nothing, exist for a fleeting instant, then vanish, cancelling each other as suddenly as they arrived. This phenomenon defies the notion of a silent, inert emptiness, and instead paints the void as a cauldron, forever bubbling at the scale of quanta. Is this just a theory? Surprisingly, no. Quantum vacuum energy reveals itself in measurable ways. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed a hair's breadth apart in a vacuum would experience a mysterious force pulling them together. The cause? Only certain quantum fluctuations can fit between the plates, while the rest exist outside, resulting in a pressure difference that pushes the plates together. Decades later, the Casimir effect was measured, confirming that vacuum energy shapes force in the physical world. Tiny shifts in the electron's energy in a hydrogen atom, the so-called Lamb shift, are caused by the interplay between electrons and vacuum fluctuations. This subtle effect, unexplainable by classical physics, matches quantum predictions perfectly. When an excited atom emits a photon and returns to a lower energy state, it does so not in isolation, but, according to quantum theory, prompted by the restless fluctuations of the vacuum itself. These are not stray curiosities. They are the signature of a universe built on restless, irreducible uncertainty. Even the mass and charge of particles are not fixed properties, but sculpted, at least in part, by their interactions with the vacuum's quantum soup. Zoom out and the stakes grow even higher. According to Einstein's E equals mc squared, energy and mass are interchangeable. If vacuum holds energy, it also holds mass, the so-called vacuum energy or cosmological constant. In Einstein's equations of general relativity, the cosmological constant acts like a kind of repulsive force, opposing gravity and influencing the expansion of the universe. Cosmologists discovered that the universe's expansion is accelerating. The best explanation? Dark energy, a phenomenon perhaps driven by the energy of the quantum vacuum. Yet here lies a mystery. The value predicted by quantum theory for the vacuum's energy is vastly larger than the value observed via astronomical measurements, by a factor of 10 to the 1/20th power, the largest known discrepancy between theory and observation in science. This puzzle is known as the cosmological constant problem, a deep riddle that continues to perplex physicists. Does the vacuum energy truly drive cosmic evolution? Does it shape the birth and fate of everything? The question remains, drawing researchers to probe ever deeper. If empty space thrums with limitless energy, why can't we tap it? The dream of extracting zero-point energy has inspired both serious research and wild speculation. However, the reality is grim for would-be energy miners. The energy is absolute, omnipresent, and can only be felt as a difference, the way the Casimir effect manifests. As of now, there is no known way to exploit this energy for limitless power without violating conservation laws or the structure of quantum field theory. Still, engineers are exploring the vacuum as a frontier. The Casimir effect, vacuum polarization, and tiny quantum fluctuations all play roles in the next generation of nanoscale devices, sensors, and quantum computers. The idea that empty space is not truly empty, and that the universe is never truly at rest, opens philosophical chasms. Are all particles and forces but excitations above this background sea? Is reality ultimately a play of energy on top of an unknowable stage, full of hidden potential? Some quantum theories even suggest the vacuum can influence the motion of macroscopic objects, as measured in experiments with gravitational wave detectors like LIGO. Others hint that the structure of space-time itself is a consequence of vacuum energy, tying the very geometry of the universe to its quantum undercurrents. Negative and reverse time, where the quantum clock runs backward. Settle in and close your eyes. Picture the deepest void between stars, a darkness so absolute you could believe in nothingness. Yet it is here, in the emptiest reaches of space, and in the tiniest trembling of atoms, that quantum mechanics lays its strangest trap, the possibility that, in its secret machinery, time can move in reverse, or even become negative, where effect appears before cause, and particles seem to outrun the future. For most of human history, time has been an arrow, ever marching forward, from past to present to future. The universe seems to follow this rule. You remember yesterday, not tomorrow. Ashes drift from the fire, never back into wood. Cold tea never grows hot by itself. Cause precedes effect. But quantum mechanics, the physics of nature's smallest scales, has always been a rebel in time's domain. Not only does it flout all expectations about certainty and position and logic, it has begun to challenge the very sequencing of events, revealing, in the right conditions, flashes of negative or reversed time. The most astonishing demonstration of negative time unfolds not in science fiction, but in laser-lit labs at the heart of modern quantum research. In 2024, a team from the University of Toronto embarked on a bold experiment. Their stage, a cloud of ultra-cold rubidium atoms chilled near absolute zero, a cosmic fog in which light could wander and be transformed. The script was deceptively simple. Fire a series of photons, tiny packets of light, into this atomic cloud and measure two things. How long do photons take to traverse the material? And, just as importantly, how long do the atoms themselves remain excited after absorbing and re-emitting those photons? Classically, the answers should always be positive. The light is delayed by the atoms, and the atoms stay excited for a positive, measurable time. But in quantum mechanics, nothing is ever so clear. What the team found defied intuition. In certain conditions, the measured excitation time for the atoms, a measure of how long they linger in this energized state, was not just short or fast, but negative. Quantum clocks, rigged to count this period, seemed to run backward, as if the atoms began to return to their normal state before the photons had even arrived. Even more dramatic, some photons appeared to exit the atomic cloud before logically, causally entering it, meaning they left the material before arriving. Imagine this with cars and tunnels. It's as if you send 1,000 cars through a tunnel, but on average, some seem to emerge before they actually enter. Or, tuning a quantum clock, you watch its hand tick in reverse as though defying the very rules you set to govern it. In quantum physics, everything is probabilistic. Position, energy, even time itself can be smeared out, blurred across a cloud of possibilities, rather than marching cleanly from cause to effect. When researchers measure how much time a group of photons spends exciting a group of atoms, they aren't pinpointing a timeline for a single particle, but averaging over all paths and processes, some of which give mathematically negative values. How does this happen? At the quantum scale, the act of measurement, the form of the experiment, and the statistics of waves crossing waves can make it appear, in very real, measurable ways, that an effect precedes its cause, or that particles skip ahead in time. This isn't true backwards time travel like in the movies, but it is far stranger. It's reality allowing, under precise conditions, a negative interval between steps. Beyond the Toronto results, researchers around the world have begun to test what happens when you actively try to reverse time for quantum particles. A group in Austria used a quantum switch, a sophisticated arrangement of crystals and mirrors, to force photons effectively to retrace their steps, restoring them to a prior state as though rewinding the film. They dubbed this idea a rewind protocol, not mere mathematical magic, but actual manipulation of quantum systems so they behaved as if time ran backward. In these setups, individual photons, particles of light, can be fast-forwarded or rewound, losing or gaining age at the experimenter's whim. This isn't time travel for people, but it's the strongest evidence yet in a laboratory that the error of time at the quantum level is not guaranteed. So does this mean we can send messages into the past or undo mistakes at will? Physicists caution, no. The negative times recorded don't violate causality or allow for paradoxes in the macroscopic world. They describe limits and oddities of wave and probability, not literal reversal of the universe's timeline. Still, these discoveries define the stone-carved assumptions time moves only forward. The phenomena are tied deeply to measurement and the fundamental indeterminacy of quantum states. Atoms and photons take shortcuts drawn by quantum statistics, producing measurable effects that, for the briefest moments, make time appear reversible or even negative. In experiments such as those with group delay in atomic clouds, it's not individual particles living backward, but the summed behavior. Analogous to finding the average exit time for cars from a tunnel is earlier than the average entry time. The wild mathematics works because quantum fields permit negative values in these global properties, even if each piece technically obeys the local arrow of time. Why probe these paradoxes if backward time isn't strictly real? Because twisty quantum timelines have practical consequences. Understanding negative and reverse time could improve quantum memories, help design safer, faster data transfer in quantum communications, or offer new visions for quantum sensors that can amplify the faintest signals by rewinding quantum changes. Perhaps most profoundly of all, these results provoke us to rethink time's role altogether. Some interpretations of quantum mechanics, including the two-state vector formalism, treat past and future as intertwined, with measurement outcomes influencing both directions. Others imagine time at the foundation to be emergent, a macroscopic illusion built from fundamentally atemporal quantum processes. At its heart, the discovery that time can be negative or reversed at the quantum level reminds us how much remains unknown. Should we abandon all trust in the arrow of time? Certainly not. At our scale, cause and effect reign. But as you shrink down to nature's finest threads, the world refuses to be pinned. This isn't science fiction, it's an open invitation to wonder and humility. In physics, as in life, boundaries we thought were absolute become porous, and even the march of time can, for an instant, hesitate and step backward. As our exploration draws to a close, remember that the quantum realm is not just a place of equations and experiments. It's a profound invitation to rethink reality itself. Each strange phenomenon we've seen is a thread in a cosmic tapestry more intricate and beautiful than any classical dream. From spooky action at a distance to particles that blur identities and challenge time's arrow, quantum mechanics asks us to embrace uncertainty, marvel at the unknown, and see the universe not as a fixed machine, but as a living mystery. Let the echoes of these quantum wonders linger as you rest tonight. May they inspire awe, curiosity, and humility, reminding us that the deeper we look, the more the universe invites us into its strange dance, a dance without certainty, but full of infinite possibility.